Welcome to the TAMGeF Touch-MidAir-Gesture framework. I am Alfredo Zellick.
And I'm Stephen Ignetti.
And we were led by our mentor, Francisco R. Ortega, sponsored by Naftali Richer, and our instructor throughout the semester was Masoud Sajadi. The TAMGeF framework, which we will call TAM for short, is a framework for developing applications with input devices outside of mouse and keyboard. We plan on introducing a wide range of input devices such as the multi-touch, the gyroscope, and leap motion. Our goal is to have an API that will allow developers to use these input devices easily in their own applications. The current system provides only a finger painting visualizer. This is just a blank canvas where the user runs their fingers through that canvas and the visualizer displays the movements of the fingers. It also introduces a record and playback functionality. However, that is all it does. Clearly, it's limited to only touchscreen devices and lacks any data analysis or algorithmic visualization. In our version, the TAM Visualizer version 2.0, we expanded the device compatibility to the gyroscope, introduced 2D and 3D visualization for both the gyroscope and multi-touch visualizers, and in the multi-touch visualizer, we also added algorithmic visualization, things like Circumcenter calculation, averaging of points, and the shortest Hamiltonian path. Throughout the semester, we used the Agile Methodology. We had 5 sprints in 2-week iterations, where we covered many of the major user stories. In Sprint 1, the major user stories we covered involved setting up the development environment and to begin familiarization with the API. The multi-touch visualizer was modified from the original finger painting to finger tracking. We also had a new visualizer format added, which we changed the CSV file to a JSON file in the multi-touch visualizer. In Sprint 2, the major user stories that we covered was having the gyroscope code converted from Python to C++. We also introduced an aviation style indicator, which measured pitch, roll, and yaw for the gyroscope visualizer. We introduced circle connectivity for the multi-touch visualizer, and we also improved the real-time playback. Originally, there was a lag, and now it is more like a real-time recording. In Sprint 3, we had the introduction of the 2D visual aviation style dashboard. This took the Sprint 2 release and converted it into 2-dimensional format, where we could see the actual attitude, the heading, and the acceleration gauges. Also, the gyroscope was successfully connected into this aviation style dashboard. For the multi-touch visualizer, we had a complete remodeling of the internals, where most of the Qt code for rendering the graphics was converted into OpenGL. Throughout Sprint 4, we had a large collaboration with both of the team members. Me and Stephen worked on developing a 3D visualizer for the gyroscope. We also fixed a very big issue with the multi-touch visualizer in terms of the threading. Also, we had a gyroscope visualizer portability issue which was fixed. As you can see, this sprint was plagued with bugs, and so a lot of the time went into fixing those bugs. Sprint 5 is the release sprint, and throughout this sprint, we wrapped up both of the visualizers. This included refactoring code, fixing bugs, wrapping up documentation, and completing our system testing, which was most of the unit testing that we had left over for features such as the algorithms in the multi-touch visualizer and the rotation mapping for the gyroscope visualizer. Let's cover some of the system design architectural patterns. The visualizer lended itself very nicely to the model view controller architecture. We have the user interface acting as both the view and the controller. The user can see the output of the data as well as change the settings for both the gyroscope and the multi-touch visualizer. And our model system deals with taking the incoming data from our devices, whether it be gyroscope or multi-touch, manipulating the data in some way, and sending it to a visual rendering subsystem. For this project, we had many hardware and software requirements. As you can see here, we had the gyroscope, of course, a multi-touch monitor, the laptops that we were using, as well as many of the software, which would include the API for the gyroscope, the OpenGL framework, Qt framework. All of the things that were necessary in order to complete this project are listed here. We will now cover the class diagrams for both the multi-touch visualizer and the gyroscope visualizer. To begin, we'll cover the multi-touch visualizer. The visualizer main window is a capsule for the GL window. The GL window gathers most of the touch events and draws the results to the screen, which is the main window. Then we move on to the processor thread. The processor thread is the part that deals with the algorithmic analysis. This sends all the draw commands to the GL window, which is then passed on to the main window. All of these are connected to the debug window, and like a console, it displays all the errors and information to the developers. Let's begin now with the Gyroscope Visualizer class diagram. Here we have also a main window. This is also a wrapper for the Gyroscope Visualizer itself. The Gyroscope Visualizer contains two primary widgets, which are the Aviation dashboard and the GL window. The Aviation dashboard contains the QCompass, QADI, and QXL gauges, as well as an output panel, which is the Q value list view. The main window also includes the GL window. This is what renders the 3D visualization onto the main window. And we also have the gyro thread, which deals with taking input data from the gyroscope, manipulating it, and sending it out to both the GL window and the Aviation dashboard. Let's talk now about the algorithms involved in this project. We will cover things about the quaternions, Euler angles, and rotation matrices, followed by the circumcenter calculation, the minimum spanning tree, and the shortest Hamiltonian path algorithm. To begin, we'll discuss the quaternions, Euler angles, and rotation matrices. The gyroscope sends raw data to the program. We then do Kalman filtering to remove gyroscopic drift. However, it is almost impossible to completely remove the gyroscopic drift, so there will always be some sort of gyroscopic drift. The data that's sent to the program is in either quaternion form or Euler angle form, but it does not have rotation matrices. So a lot of time was spent into creating a small library to interchange between quaternions, Euler angles, and rotation matrices for the gyroscope visualizer. All of this was used to successfully map the rotation data onto an on-screen 3D visualization of the gyroscope, as well as the Aviation dashboard. Moving on to the Circumcenter calculation. This is what is used in the multi-touch visualizer to compute the circle encompassing all of the points. We compute the circumcenter for any 3 given points. There are at most 10 choose 3. And we then take the center of each one of those circles, average them together to get the average circumcenter, and we do the same with the radius. This is then displayed, and we have our Circumcenter. We also have the formulas here for reference. Let's cover now the minimum spanning tree. What this does is, given a graph, which includes some set of vertices and some edges, we'll find the tree connecting all of them with minimum weight. Here we have uniform weight. So what we do is a variation on minimum spanning tree, and we just show a connected tree of all the vertices. We now move on to the shortest Hamiltonian path. What we do here is a dynamic programming approach on the fingers shown in the visualizer. We treat it as a graph, and we run the standard Hamiltonian path. Let's move on to system testing. For the testing, we use the bottom-up approach. This means that our classes were developed separately, away from the rest of the system. We then integrated the classes by pairing each of the classes with the already tested classes. Of course, if they failed, then we would go back. If they succeeded, then we would successfully integrate this into our project. We used unit testing for the more complicated algorithmic tasks, such as the conversion from Euler angles to rotation matrices, quaternions to matrices, the circumcenter calculation. All of the algorithms that we spoke about underwent rigorous unit testing. This concludes our presentation, and following this will be a live demonstration of both the multi-touch and gyroscope visualizers. We hope you enjoyed it. Thank you very much. I will now demonstrate the gyroscope visualizer. Here on the leftmost gauge, you will see the pitch indicator as we go up and down, the roll as we roll from left to right. We also have the compass going here west. Now we're going south, and we go all the way around. Then we have the accelerometer. If I shake it up a bit, you'll see it goes up, and as soon as it slows down, it reduces. Now let's check out the 3D visualization system. Here we have a direct mapping of the gyroscope on screen. Going up, going down, left, and that is how the visualization system works for the gyroscope visualizer. We will now be moving on to the multi-touch demonstration. Now we will introduce the multi-touch TAM visualizer. First off, let's look at the finger averaging algorithm. Here we notice the average point in the middle connected to all the other points. Now let's look at the minimum spanning tree algorithm. Here we visualize the minimum spanning tree of all the fingers, and as we add more fingers, the connectivity remains proper. It is still a tree, and it is the minimum such tree. Now let's take a look at the circular connectivity. We find the circle passing through all the points on the screen at the moment. So we add more fingers. Here we have all 5 fingers, and the circle has been appropriately found. Now let's move on to the shortest Hamiltonian path. This will give us the shortest path between all of the vertices. As you can see, as we extended, here we have a slight bit of an error, but this is corrected and will be corrected in later editions. And last but not least, we have refactored all the code into OpenGL, and we have now OpenGL cubes. So instead of the tracking circles, now we have tracking cubes. That will be all for the TAM visualizer. Thank you so much for watching.